Hi, and welcome to our second lesson about solving exponential and logarithmic equations. Today we're going to be focusing on some application problems because really lots and lots of application problems can be solved with exponential or logarithmic equations. They model a lot of what happens in the natural world. If you think about applications that you do with exponentials, you have to think about population growth because that's not a linear model. Things tend to grow quickly, more quickly than in a linear rate. So exponentials fit that type of application very, very frequently. So let's take a look at this. The formula A, capital A, is going to model the population of California in millions of people. Is equal to 36.1 e raised to the 0.0126 t, where t is the number of years after 2005. And to help us think about this model and what its pieces really mean, I have a series of questions for you. What was California's population in 2005? Well, that's when we start counting in this one. So many people would refer to that as the starting point, and that's the way I talk about it a lot. It's that 36.1 million that we're talking about initially when the count started. That's how many people were in California. What does the formula predict for this year, 2013? Well, if you think about that, how many years have gone by? The amount of time would be equal to where we are now minus when they started counting, which was 2005, and folks, that's 8 years. So let's take a look at this formula evaluated at a t of 8. What we need is to find the number of people starting with 36.1 million times e raised to, and then here comes our exponent, 0.0126, that's the growth rate, if you will, and we multiply that by the number of years that are gone by since 2005, and that would be 8 years according to what we just said. I want to get my calculator showing here, so excuse me for just a minute, and let's put that into the calculator. 36.1 times e, and on your calculator that will be the second of the natural log key, because e is the base of those natural logs. Most calculators open up a place for you to enter an exponent, and that's what this one does. 0.0126 times 8. As long as that's all up in the exponent place, I'm good. I don't need any other parentheses or anything. And when I press enter, my calculator is going to tell me that in 2013, based on this model, there should be around 39.9 million people in California. Good, so that's what we're looking at. The next question asks us to solve an exponential equation, which is what this unit has been about. So let's see, the population, we're interested in when it's 45 million. Well, that's A is that. So we want to solve this equation. 45 equals 36.1 e to the 0.0126 t. We don't know how long it will take. That's what we're trying to find. So if you think about this, folks, this is an equation like any other, except this time the variable is in the exponent. So if we isolate that exponent term as much as possible, that'll help us. Let's divide both sides by 36.1. So we're talking 45 divided by 36.1 equals e raised to the 0.0126 t power. One of our techniques for solving exponentials was to take the log of both sides, natural log here, since we have a base of e. So I'm going to do that. I'm going to bring my work over here. I'm going to take the natural log of what was on both sides, so that would be 45 over 36.1 equals the natural log of, oh wait, I forgot. We got to do that power rule. Applying the power rule brings the exponent down in front, so 0.0126 t times the natural log of e. And then I think to myself, well, one of those strange log identities was the fact that the natural log of e is equal to 1. So really, this is saying that if I take the natural log of 45 divided by 36.1 and then divide it by 0.0126, I'll have the amount of time required. So here comes my calculation. T is going to equal natural log of 45 over 36.1 all over 0.0126. And as I've said before, I'm not going to go to my calculator until I have it solved for my variable. Now's the time to go there. Natural log opens up a parenthesis, 45 over 36.1. Close that parenthesis because we want that whole value divided by 0.0126. And this should give us the number, well, let's see. Here's what it says. T is about 17.5. Around 17.5. And you think to yourself, well, what's that stand for? Well, we said that T is the number of years after 2005. So if we add 2005 plus 17.5, that would give us 2022.5. Somewhere around the year 2022 is when California's population will reach that level. That's if this model continues to be a solid one, which may or may not be true. 2022 is quite a ways in the future, so things could be changing in California. In fact, they could have been changing since this problem was written, but that's our approximation. So we're going to say somewhere around the year 2022 is where they should hit 45 million. Good. Let's go on to our next application. We're going to talk about a model, a general model for exponential growth and decay. And we already have used this model in the previous problem. This is what it looks like. The amount of whatever it is that you're calculating will be equal to the original amount. So A sub O, that's the starting point or original amount, times E, very often natural logs work best in these kinds of problems, times E raised to the KT. Now, as far as deciphering the formula, K is either a growth or decay rate, which will be different for every application. Growth or decay rate. T is the number of time periods, usually measured in years. I'm going to just write number of time periods though, because it isn't always years. But that's the model for any exponential growth and decay situation. The amount of the thing you're watching will equal its initial amount times E raised to the growth rate times the number of time periods that have passed by. Let's see if we can apply that. In 1990, the population of Africa was 643 million. And by 2006, which by the way, how many years is that? It's looking like 16 years to me. In 16 years, they had grown to 906 million. This says that we should use the exponential growth model to find the growth rate. Folks, that is, we're going to look at a specific example for populations in 2 different years and use it to find a value of K. Then we can use the value of K to continue making predictions about the situation. But for us to get it, we're going to remember the growth model. And it says that the growth that you have now, and the now for us is 2006, 906 million will be the same thing as what you started with, 643 million, times E raised to the KTth power. And T here is 16 years. We want to solve this for K, folks. We're looking for the growth rate. And you're going to see the same kind of algebra in all of these problems. We want to isolate the term with E in it. So we're going to divide both sides by 643. 906 over 643 will equal E raised to the 16K power. And once we're here, we know the next step, because we just did this a minute ago, is to take the natural log of both sides. So we're talking the natural log of 906 over 643 will equal, you bring the exponent out front using the power rule, 16K times the natural log of E, which we already know to be 1. Now to solve our problem, K will equal the natural log that we had, 906 over 643, divided by 16 in this case. Let's get that calculator out and let's see what we can come up. Alright, let's go to our calculator. We know we need the natural log of, and it is 906 divided by 643. Then we need that quantity divided by 16. And apparently our growth rate is about 0.0214, right around 0.0214. So they are growing. Okay, that's looking like about 2% per year. By which year will their population reach 2,000 million? Okay, we had it at 906, but we started at 643. So we are looking for the year when their population reaches 2,000 million, or 2 billion. And according to our equation now, that would be 643 starting point times e raised to the, we know k because we just solved for it, 0.0214 times t. This time we're looking for the number of years, and the solving process is what we've already done. So I'm going to say I know what's coming. It's going to be the natural log of 2,000 over 643 equaling the natural log of, whoops, I forgot, I need to do the power property. See, we'll do this enough that this will become second hand to us. We'll know exactly what to do. You bring the exponent out front, 0.0214t times the natural log of e, and the natural log of e is 1. So that's going to go away. To find the answer to our question, then we need to take that natural log of 2,000 over 643, and we need to divide it by the growth rate, 0.0214. What that's going to get us is the number of years after 1990 that the population will hit 2,000. Alright, let's see. I'm going to minimize this a little bit because I need to be able to see my calculator. And excuse me while I draw this down. Alright, okay. So I'm going to take the natural log of, here she goes again, 2,000 divided by 643, the starting place. And remember, those were both millions of people, divided by a growth rate of a little bit more than 2% per year. And according to this formula, if our prediction, if their population keeps growing at the same rate, it will take about 53 years. T is around 53. Now, as far as making sense out of it, the number of years past 1990. So if we go 1990 plus 53, according to this formula, in about the year 2043, their population will reach 200 million. $2,000 million. Or 2 billion people. It's a lot of folks. But that's a good problem that demonstrates how to use that exponential growth and decay model. Let's go on and see what else we have for us today. So we've talked population. Oh, now we're going to talk half-life, I'm pretty sure. Strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones, which is kind of chilling when you think about it. You don't get a say in that. Since it's in our atmosphere, it's part of us. The half-life of strontium-90 is 28 years. That's going to be important for us. Use that information to find the exponential decay model for strontium-90. I just want to remind you again, the growth model that we're using says starting amount times e raised to the kt power. And in this problem, we know the t is 28, and that 28 years is what it takes for an original amount to be half as much. So if you think about the original amount as half, or I'm sorry, as all, as in 100% of, what we want is 50% of it left. Or let's substitute a 50%, 0.5, for the amount in the atmosphere if we started with 100% of it, or 1, times e raised to the, K is what we're looking for here, but we know the half-life is 28 years. So there's an equation that will let us find the value of K for this particular half-life problem. You know what's coming next. We're going to divide by 1, which is really meaningless. So then we're going to take the natural log of both sides, and we'll say the natural log of 0.5 is equal to 28K. Now, I've been writing all along natural log of e. I'm not even going to write that this time because I know that that's the same thing as 1. So the work that I need to do to find k then would be to divide the natural log of 0.5 by 28. This will get me the decay rate of this strontium-90. So K, according to this, the rate of decay is about negative 0.0248. You guys, that makes sense. Since decay means it's going down, the K value is negative here. So now we can write the exponential model for this. For this particular chemical, A will equal A sub O times e raised to the negative 0.0248 t. And that model can be used to solve problems about strontium-90 in our atmosphere. Suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for the strontium-90 to decay to a level of 10 grams? You guys, the thing that's going to hurt us the most here is remembering A sub O is what you start with in this problem. That's 60. A is what you want, and we want to know when it gets to 10 grams. So let's fill into our equation. 10 will equal, and it is the starting amount, 60, times e raised to the, here's where our decay rate comes in, negative 0.0248. And we're looking for the number of years it takes for this to happen. So now we have an exponential equation to solve, and we've been doing this all along. So we want to get that e term by itself, 10/60ths. And we know that we're going to take the natural log of both sides. So I'm going to write that in here. The natural log of 10/60ths will be equal to, power rule says, bring the exponent down, 0.0248t. And then it's times the natural log of e, which we know is 1. So here's our problem. To find the number of years, we need to take the natural log of 10 divided by 60, or 1/6, and that needs to be divided by negative 0.0248, or about 2% per year, 2.5% per year is how much it goes down by. Let's see. Whew, that is a long time, folks. Around the time required for us to get to 1/6 is around 72.2 years. Okay? I think that deserves a little sad face. Okay? We don't want that happening to us. All right, one more problem for us to think about, one more type of exponential or logarithmic problem. Go ahead and clear my calculator here. Newton's law of cooling. So this is more of a science question, and you know science is not my favorite. The temperature that some substance is equal to room temperature, which we're going to call C, plus the substance's initial temperature minus room temp, right? That's how hot it was above normal, times E to the KT. And K is different for each substance. T is equal to usually a time period, minutes is what we're going to talk about in here. So T is going to stand for the temp now. C is room temp. T sub 0 is the starting temp. And K, again, is a cooling rate that's different for each substance. T is a number of minutes, usually. Okay. All right, so let's take a look at that. An object, it says, is heated to 100 degrees. You guys, that's the starting temperature. That's our T sub O. It's left to cool in a room that has a temperature of 30 degrees Celsius. So this is our C, that's room temp. After 5 minutes, so here's the time that we're looking at, the temperature of the object is 80 degrees. So this is the now temperature, or just T, this one. Use Newton's law of cooling to find the value of K for the object. Okay, we can do that. The temperature now is 80, and that is a result of, we had a room temperature of 30 plus the starting temp, which was 100, minus 30. If you think about that, folks, you're adding room temperature here and subtracting it here. That seems kind of defeating the purpose, and so I'm sure some of us are going to think about that. Well, maybe we don't have to. Oh, but wait, we do, because see, this is hooked with multiply to E times the K, and we're talking 5 minutes, right? So we can't just say that it's 70 here. That's not going to work for us, and it's because of that multiplication. Well, let's try and get the exponential term isolated. So we will subtract 30 from both sides, and now we're looking at this. 50 is 70, so I'm going to subtract just because I know what that is. E to the KT, K times 5 in this case. We want it isolated, so let's divide 50 by 70, and I'm going to come over here. 50 over 70 will equal, and that was E raised to the 5K. Well, by now we've done this so much, we know exactly what's going to happen. We're going to take the natural log of both sides. We're going to use the power property. So it's the natural log of 50 over 70 will equal 5K times the natural log of E, but that's just 1. So if we want to know the value of K, that is the cooling rate for this substance, we want to divide by 5. Natural log 50 over 70, all divided by 5 will get us our K. And now it's to the calculator. Natural log 50 over 70 divided by 5 minutes says that our cooling rate is around 0.0673. Alright, so we're going down, so that should be negative. The temperature after 20 minutes. Alright, now we're going to use an exponential model based on this K. So what we want to know is what the temperature is afterwards. So that's the A thing. That's our unknown. Where we're starting 30 plus, we had it up to 100. 100 minus 30. I'm going to just put the 70 in there. E raised to the, we know K, negative 0.0673, and 20 minutes. We know the time. So here's what we've got. Now it's just a matter of doing the arithmetic. And since this is the variable that we're interested in, we just got to plug this into our calculator. So 30 plus 70E raised to the negative 0.0673, all up in the exponent. Folks, if your calculator doesn't put you all up in the exponent, you're going to want to put parentheses around that. It'll take it after 20 minutes. That temperature is going to be, according to this formula, around 48.2 degrees centigrade. All right, now we have a similar question. This time we're solving for a specific temperature. How long before it hits 35 degrees centigrade? So the A is 35. That's where we want to end up. We start at 30. That's plus 70E to the negative 0.0673 T. And we're going to do the same kind of manipulation that we did just a moment ago, subtracting out 30. And if we subtract 30 from both sides, we get this. 5 is equal to, so that's the amount of change we're looking for, right, from room temp. 5 will equal 70E to the negative 0.0673 T. divide by 70. So 5 over 70 is equal to, and use the power rule. See, this is going to end up being a natural log. I'm going to go ahead and put it. Okay, natural log of 5 over 70 equals, and it will be negative 0.0673 t. So to find t, the number of minutes that it takes, we're going to take the natural log of 5 over 70 and divide it by that cooling rate, which is negative 0.0673. All right, according to this, our time that we'll need to wait is right around 39 minutes, about 39.2 minutes to be precise. Good. So we've used our exponential equations and logarithmic equations to solve some real-world problems. We're going to ask you to get out there, try that U-Try right now. Remember, it's due before the next class period, and I hope you have a great night.